Okay, it's nice to see the room filling up. It's the top of the hour, so I think we'll go ahead and get started. Just a few housekeeping announcements. So first off, welcome everybody to the SZ4D International webinar series. This is a series that has focused on highlighting work by international groups focused on one of our three main areas: faulting and earthquake cycles, magmatic drivers of eruption, and landscapes and seascapes. Today's is the second Magmatic Drivers of Eruption International webinar. The next one, I believe, coming up on November 20th will be from the Faulting and Earthquake Cycles group, and that'll be Kellen Wang. You can find information about the initiative and about these webinars, including videos of past webinars, on our website, SZ4D.org. So please both go check out the talks we've had and keep an eye out for announcements of future webinars. These have been really great. I also want to mention it's a busy and exciting time for SZ4D. So I just want to mention another upcoming event that should be of interest, and that is a town hall next Friday, which is formally linked to GSA, and we will present some updates on the SZ4D activities. You do not need to be registered for GSA to register for our town hall. So I would like to encourage you to come and participate. And it'll be a chance to ask questions and provide your input to the initiative. So again, you can find information and registration links at our website, SZ4D.org. With that, it's my great pleasure to introduce today's speaker, Dr. Silvana Hidalgo, who is the Jefe de Departamento de Geofísica at the Instituto Geofísico of the Escuela Politécnica Nacional in Ecuador. Silvana leads a group which is in charge of monitoring over 25 active volcanoes in Ecuador. And as you'll hear, they've had some very interesting experiences recently with these eruptions and very exciting research progress as well. So we look forward to hearing about the Ecuadorian Volcanic Arc, a wide perspective. And just before I turn it over to you, Silvana, I want to offer our congratulations on behalf of SZ4D to you and your group for winning the 2020 IAVSE Award for Volcano Surveillance and Crisis Management. This is a big honor, and no doubt, as you in the audience will see from this talk, very well deserved by Silvana and her colleagues at the IG. So congratulations, and I will turn it over to you. I think Harold or Natalie can stop the screen sharing, or no, we've got Silvana's. So just before, one more note, if I can ask everybody in the audience, please to mute yourself and turn your cameras off. If you have questions, we're going to save them till the end. Please type them in the chat box. And once we get to the end, I will go through and read through them in sequential order so that we can have Silvana address them. So please feel free to enter questions throughout the talk, but we'll get to them at the end. Okay, and now Silvana, I will turn it over to you.
Okay, good morning, good afternoon, everybody. Thanks a lot for inviting me and the IGEPN to this international webinar series. It's really important for us to be able to show part of the things that we have done in the last decades in Ecuador. So I will rapidly start by mentioning that there's a lot of people working in Ecuador in volcanoes, in the volcanic arc, and I hope I put all the names. I apologize if I didn't, but we are several people from the Instituto Geofísico, but also from different universities, especially from France, working in the first part that I will present today, and then I will introduce other groups also. So, Ecuadorian Volcanic Arc, a wide perspective. I will split this talk in three different parts. So at first, I will talk about the geochronology of the arc. Why? Because it's, of course, important to know since when the arc segment actually developed and acquired the present configuration that we have nowadays. In a second part, I will talk about the geochemistry of the magmas. And I will make just a rapid overview about the main geochemical characteristics and actually try to get insights into the magma sources. And at last, but not at least, I will talk about the recent volcanic activity in the last 21 years since our volcanoes become active. So I will start by showing you the geodynamical setting of Ecuador, which is quite complex. So you can see here in this map, we have the subduction of the Nazca Plate, a young oceanic plate below northern South America. The age of this plate is around 10, 20 million years. And interestingly, it carries this Carnegie Ridge, which is an aseismic ridge produced by the activity of the Galapagos hotspot. We also have this fracture zone called the Grijalba fracture zone, which is dividing the northern young part of the plate from the older crust to the south. Also, in the recent years, from seismic studies, we also know that the subducting slab, as you can see in these yellow dotted lines, has variations. The geometry of the subducted slab has variations below the Ecuadorian arc. So all of these things in the subducting plate makes this context quite complex. But not only that, we only have a crust that is quite complex too. We have an heterogeneous crust, which is actually quite thick, about 50 kilometers in the more thick part of the crust. And we also have different lithologies, so the terrains are not homogeneous. So we have to the west, here in blue, more oceanic affinity terrains, and then to the east, we go to more crustal-like rocks. So we were able to define actually 4 different rows: the Western Cordillera, where you can see the volcanoes that are in blue, the Interandean Valley with the volcanoes which are in yellow, the green volcanoes which are built above the Eastern Cordillera, and the back arc where we have the volcanoes built above the Subandean zone. So complex subduction zone, complex crust above this subduction. So just to start with this geochronological part, it's important to note that in Ecuador we have volcanic edifices. So we have been recognized more than 85 in the last years. And this is a very short segment of the arc. We are talking about 300 kilometers by, in the largest part around 500 kilometers large. So it's interesting to know how much time this arc took to get developed in its present form. So for this, there have been several projects aiming to date the volcanics in Ecuador. At first, the geochronological work was performed in the 80s, and Barbary and colleagues in 1988 already published 25 whole rock potassium argon ages that were kind of giving the first insights into the age of the arc. Since then, the IRD, together with the IGAPN, produced several datings for individual volcanic centers in order to understand actually the evolution of individual volcanoes. From these studies, we had around 50 whole rock argon ages, and they were mainly focused, for example, in Cayambe, Pichincha, Atacazo, and in the southern part of the arc. Nevertheless, in the recent years, together with the University of Paris Sud, and under the direction of Pablo Samaniego and Xavier Kidler, a very ambitious program of dating the volcanic arc was enterprised. And we work in the northern part of the arc, in the central part of the arc, and to the south. And these parts of the arc have been dated through 100 new potassium argon ages performed on ground mass. And this is part of the PhD work of Mathilde Bablon and Santiago Santamaria. This last one is still ongoing, so we hope we will have even more ages in the future. So if we put together all these results, we can start to answer to some of the questions about the age of this volcanic arc. So we can see here that the oldest volcanic complex is the Chacana volcano, which is around 1.3 to 2.7 million years. And these ages are from 2006 from the work of Updike and co-workers. The data that we start to acquire actually shows that an important part of the oldest volcanoes is actually starting in the northern part of the arc. And the oldest volcanoes are the basal parts of the edifices like Pichincha, Atacazo, Mojanda, Cayambe, Pan de Azúcar, and Mera Lavas, and the ages are more than 1,000 kiloyears. So quite old actually, but not that old for a recent volcanic arc. Then we have some other intermediate ages, more than 700 kiloyears, and we can see the part in the arc to the north in the boundary with Colombia that start to appear with Cerro Negro. We have also some ages from Rucu Pichincha intermediate, Santa Cruz, Aguatoa to the center and part of the south of the volcanic arc, and also some ages for Cerro Negro to the north that are starting to appear. Following this, we have maybe the more intense part of development of the arc. It's in the last 600 kiloyears. And we see companion volcanoes like Chiles appearing in the north, Fuya, which is a companion to Mojanda volcano. Intermediate part of Atacazo is also there. Iliniza, which seems to be a very old volcano, is actually not that old, less than 350 kiloyears. And the part of the south of the arc is starting to be quite much populated with volcanic edifices, with Cariguairazo appearing, Igualata, the last volcano to the south of the arc, which is Sangay, and also Huizla and Tungurahua are starting to appear in this part. So these edifices, quite well known, actually are less than 500,000 years. Cotopaxi is also in this group, and Antisana, Sumaco in the Amazonian basin, and the youngest part of Nevado Cayambe. The last part of these volcanoes, or the youngest edifices, are less than 200 years old, and we have at this time almost all the volcanic activity, the volcanic edifices, perfectly configured at its present shape. So we have the youngest part of Chimborazo, the young Puñalica volcano, youngest part of Cotacachi, also Huaypichincha, Imbabura, also a very young volcano, Chalupas Quilindaña, Mulmul, and Licto. So as a kind of global conclusion, we can say that the evolution of the arc started with the volcanic edifices in the northern part of the arc, and the ages are around 1 to 1.5 million years. These are actually contemporaneous with volcano-sedimentary sequences of the Interandean Valley. Then most of the stratovolcanoes have developed during the last 600, 500 kiloyears, and at this time, the volcanic arc already acquired this present configuration. So we have the two cordilleras that are clearly seen in our geography. What is also really interesting is that our volcanic arc is then quite young. And to build the big volcanic edifices that we have, which are 2-3 kilometers high above the basement, the volcanic eruptive rates must be quite high. It's also interesting to know from these late Pleistocene volcanoes, and if we consider also the basal surface of the edifices, that the maximum number of the higher density of these edifices is just above the trace of the Carnegie Ridge below the arc. So it's interesting that this high density of volcanoes can be actually correlated with this feature that comes from the oceanic plate getting into subduction. Also, the southern part of the arc, where all these new volcanoes or recent volcanoes are formed, is coincident with this also oceanic feature, which is the Grijalva fracture zone. Interestingly, this is also correlated with lower concentrations of ytterbium and yttrium that are also associated to the trace of the Carnegie Ridge below the arc. So a lot of things are happening there associated to the oceanic features in the subduction zone. So trying to check into the geochemical characteristics of the arc, so the second part of this talk, a lot of studies have been done in individual volcanoes, trying to understand how these magmas evolve in an individual volcano, which are the processes that are involved, fractional crystallization, magma mixing, assimilation, and this has been done for a lot of volcanoes in Ecuador. So several volcanoes have individual studies dealing with these aspects. Nevertheless, general geochemical studies aiming to understand the global configuration of the arc just started in the late 90s. And at the beginning, it was actually mainly transects going from the frontal part of the arc to the back arc, including, of course, the main arc in the middle, to understand how the geochemical parameters evolve or are changing across the arc. In recent years, actually, studies are more focused on much more geochemical parameters and trying to involve much more volcanoes to understand in a more global way what could happen. It's important to note also that in Ecuador, we don't have actually primitive samples. We haven't sampled primitive volcanic rocks. And this is actually really, it doesn't allow to understand or to study what can happen in the source of magmas. So for this, in the recent years, we also try a different approach. And besides the major elements, trace elements, and isotopic compositions, we try to analyze magmatic inclusions, aiming to get the more primitive rocks that we find in the arc, and to analyze the inclusions in primitive olivines in order to get some insights into the magma source. So I will just talk about these two parts, the last two parts, in order to see a general overview of the geochemistry of the arc. So from this graph, you can see that there are a lot of sampling that has been done in the Ecuadorian arc. And actually, since the early 90s, a very complete sampling of the Ecuadorian arc was performed in the frame of the collaboration of the IGAPN with the IRD. More than 2,400 samples have been actually analyzed for several geochemical parameters. And here you can see in this classification diagram in orange and red, the samples from the volcanic front in orange, in red from the Interandean Valley, in green from the Eastern Cordillera volcanoes, and in blue from the back arc volcanoes. So typically we have medium to high potassium basaltic andesites, and some subordinated rhyolites, mainly of calc-alkaline affinity, except for the back arc volcanoes, which show an alkaline affinity displaying high potassium. So from this graph, we can already see that we have a zonation across the arc from the west to the east, as we can separate the different rows of volcanoes, the different alignments of volcanoes in this, with this parameter. This is also confirmed by trace elements. And here we plot the trace elements compositions, especially incompatible, against the distance to the trench. The gray field represents the whole ensemble of the samples analyzed, disregarding their MG number, and the symbols actually represent the samples with an MG number higher than 55, aiming to get the less evolved samples trends. As you can see, the trends are fairly the same for the samples with higher MG number than for the whole ensemble of the samples taken in the arc. And we can see or confirm what is seen with potassium, that actually we have an increase in incompatible elements from the volcanoes close to the trench to the volcanoes that are getting a higher distance to the trench. And this has been already ascribed as in response to the lower partial melting degree of the mantle associated with lesser slab contribution as we get farther from the trench. We also plotted here some ratios of fluid mobile over fluid immobile elements, for example, boron niobium, and we ascribed this decrease from the volcanoes close to the trench to the volcanoes farther from the trench as a process of dehydration of the slab, which is actually maximum below the frontal arc. So this is what we can understand, or we have understood from the major and trace elements in the arc. And then we started to analyze isotopic composition. So we started with strontium and neodymium isotopic systems. And here you can see the plot of the Ecuadorian volcanoes, the volcanic front, the Eastern Cordillera volcanoes. And you can see the oceanic terrains that could be involved in subduction and the central volcanic zone of the Andes. You also can see the crustal Colombian xenolites that represent the lower crust and the compositions of the Western Cordillera basement. You can see in a zoom of this part of the graph that the volcanic front volcanoes, which are in orange, the Interandean Valley volcanoes, which are in the yellow field, and the back-arc volcanoes displayed quite similar compositions in these systems, strontium and neodymium isotopes, and are different from the volcanoes from the Eastern Cordillera. This is also evident if we plot these ratios against the distance to the trench, and we can actually see that the Eastern Cordillera volcanoes have higher strontium, while they have lower neodymium. This characteristic has been attributed to a crustal contamination that was estimated around 7 to 14% that is occurring in the Eastern Cordillera. And this is also in response to the nature of the basement below the Eastern Cordillera volcanoes, which are more crustal-like in nature. Nevertheless, when we analyze the volcanic front volcanoes for other isotopic systems, like oxygen isotopes, we actually were able to estimate also a crustal contamination below these volcanoes, but with different terrains with a higher composition in oxygen isotopes. In the last years, Marianne and Celan and co-workers actually did a quite amazing job in analyzing a lot of samples of the arc, again for strontium, neodymium, and lead isotopes, and they were able to see other processes that are occurring in the evolution of the arc magmas in Ecuador. So in these graphs, you can see that the Ecuadorian arc displays heterogeneous compositions in lead isotopes if we compare to the southern volcanic zone, but more homogeneous if we compare to the central volcanic zone, where we know there's much more crustal contamination. In the zoom of this chart, you can also see some of the potential participants in the genesis, or able to produce, the end members able to produce these compositions. Interestingly, in lead isotopes, we can see that almost of all volcanic front volcanoes and back arc, which are in blue and orange, display homogeneous 207, 204 lead, while they have quite important variations in 206, 204 lead compositions. In contrast, Interandean Valley volcanoes and Eastern Cordillera centers display a large number, a large range, in 207, 204 lead, with little variation in 206, 204. So with this information, with this data, Marianne performed a really nice kind of space of heat map of the compositions of the lead isotopic space. And she produced this map where you can see that actually lead isotopes are not following the same trends that were shown by strontium and neodymium. As we can see that here, these green volcanoes, which display high 207, 204, are not only present in the Eastern Cordillera, but also in the volcanic front. So there's another processes that is happening there to produce these compositions. She was also able to distinguish these orange color volcanoes that display low 207, 204, and also too low 206, 204. And they ascribe these to crustal contamination, to upper crustal contamination, while the green seem to be in response to lower crustal contamination. Nevertheless, we have another two colors here in this map, and actually they modeled these different compositions, and they were able to produce all the different variations in this data by several processes that are actually superimposed in the different volcanoes. So we have at the same time a metasomatism of the mantle by aqueous fluids, but also by slab siliceous melts. And we also have an upper crustal processing that was already seen with strontium and neodymium isotopes, but also this lower crustal processing that was really not observed before. So this was a really interesting work that she published in GCube in 2017. But as I told you before, for the more primitive magmas, Ecuadorian arc is actually lacking these kind of samples. And so we decided to work more in magmatic inclusions. And for this, our colleague Diego Narvaez is working on his PhD thesis with magmatic inclusions of the volcanoes of the arc. He already published a nice paper about the sampling of two volcanoes, Puñalica, just above the Grijalba fracture zone, and Sangay, which is built above the subducting, let's say, where the crust that is being subducting is quite old. And his results actually show that for Sangay, the main agent involved in the metasomatism of the subarc mantle are aqueous fluids, and this might be related actually to the intense dehydration of the older subducting slab below or to the south of the Grijalba fracture zone, while for Puñalica, he requires a lot of hydrosiliceous melt. Probably the amount of fluids present in this part of the fractured crust are allowing the crust actually to melt and produce siliceous melts to metasomatize the mantle arc. Diego is extending now this kind of a study to the whole arc, and we hope he will have soon results to better understand what's happening below the Ecuadorian arc at the source level of magma. So just as some conclusions of this second part of the talk, while Ecuadorian arc magmas, as all arc magmas in the world, I guess, have suffered several superimposed processes before their eruption. Fractional crystallization and magma mixing processes have shown for individual volcanic centers, and there's a lot of literature covering this kind of processes. I didn't detail it here, but it's quite well documented. Also, crustal assimilation takes place in the whole arc, despite the different basement lithologies that mantle magma traverses. Crustal assimilations occurs also in the upper and in the lower crust level, so it's at different levels that this process is taking place. And also, subarc mantle is metasomatized both by aqueous fluids and by hydrosiliceous melts. So this is interesting because at some point there was a kind of a discussion, an argument about which was the main metasomatic agent. And actually, we can have fluids, but also hydrosiliceous melts participating in the transformation of the mantle below the arc. And it's also interesting to see how this along arc zonation is also present and should be related to the presence of the Carnegie Ridge in the subducting plate. Okay, but of course, this is really nice from the perspective of understanding and better knowing what is happening from the fundamental science point of view in the arc. But when you live on a volcanic arc, volcanoes become actually active. And then you need to deal with that kind of activity because it has an impact on the population. And this, of course, is the case of the Ecuadorian Volcanic Arc. So for this, in 1983, the Instituto Geofísico was created with very few people really aiming to understand what happens with volcanoes and how the population could be protected from their activity. So the Institute, which started with, I don't know, maybe 10, 15 people, now accounts with 80 people working daily to study volcanoes, monitor volcanoes, but also earthquakes, as is our main activity, our main function for the Institute. So in the last 21 years, we had 5 volcanoes that had eruptions in the continent, but also we had to deal with volcanoes erupting in Galapagos. Of course, I will not talk about these eruptions. This is not the same context. And in order to better monitor these volcanoes, but also the earthquakes, the Institute has installed some 500 stations around the country that arrive in real time to Quito. So if we go back to our map of volcanoes, this time I will explain you the colors on this map. So we have these blue volcanoes, which are actually the volcanoes that we consider that are extinct or that will not become active again. So this is the greater number of volcanoes, around 68 extinct volcanoes. We also have 11 potentially active volcanoes, which are the volcanoes in yellow. And these are the volcanoes that had activity during Holocene times. And we have these 8 volcanoes in orange that are actually the volcanoes that had activity in historical times, which for Ecuador is the last 500 years since the arrival of the Spaniards to our country, and when we have historical reports. And we also have 2 volcanoes in activity, currently active, which are Reventador and Sangay. This map needs to be updated. Tungurahua is still in red, but now it should move to orange color. It's important to note that for these potentially active volcanoes, we have produced hazard maps. So these documents exist since the late 80s and have been evolving and been improved through time, depending on the knowledge of the volcanoes, but also on the techniques to make hazard maps for volcanic activity. All the information that the Institute produces is included in books, in triptychs that are typically done to the global population and to the authorities, of course, charge-free. And all the information is also available in our webpage, Facebook, and Twitter. And so far, we have around 1 million followers being able to see our information in real time. So these monitoring networks were designed depending, of course, in the hazard that the volcano could pose to the population. And for this, we designed 3 different monitoring levels. Monitoring level 1 is the one where we have at least 3 monitoring techniques. Monitoring level 2, we have at least 2 monitoring techniques. And level 3, only 1 monitoring technique, which is typically only a seismic station or that kind of instrument. And as I said before, all the data arrive in real time to the IGVPN in Quito through radio link, satellite transmission, microwave, or whatever media is possible. Just an example of these monitoring networks, you can see here, these are for potentially active and active volcanoes like Antisana, Chimborazo, Cayambe, and Huicocha. And you can see that we have actually 2 monitoring techniques, which are seismic stations that could be broadband stations or short period, depending on the age of the network. And we also have GPS and tilt meters in order to check the formation of the volcanic edifices. We also have better monitoring networks, as I told you before, level 1, where we have more than at least 3 monitoring techniques. These kind of networks are, of course, present in volcanoes that are active and in the erupting volcanoes. So here I show you the example of Guagua-Pichincha volcano, Tungurahua, Reventador, and Cotopaxi. Pichincha is very close to Quito, 12 kilometers from Quito downtown. So of course, this volcano requires an important monitoring network. Tungurahua is close to populations living in Baños, around 8,000 people. But when it's a very touristic place, and in a weekend we can have 25 people just at the feet of the volcano. And also there's a lot of people living here because they have a lot of outcrops and farming animals. We have Reventador volcano. It's not very highly populated. No big towns or big communities are living around the volcano. Nevertheless, the pipeline transporting oil from the Amazonian basin to the port in the coast to be exported just go through the base of the volcano. And Cotopaxi is a volcano that is that poses a very important hazard because it's an ice cap volcano, and very big lahars could be produced by its activity. These kind of volcanoes have different instruments like seismic stations, GPS altimeters, scanning DOAs, and IR and visible cameras to check for surface activity. So I will just briefly summarize the last 21 years of activity in Ecuador. And the first volcano that became active was Huayllapichincha in 1999, and its eruption lasted until 2001. The previous eruption was in 17th century, and from the descriptions that we have on this eruption, it actually put a layer of 20 to 30 centimeters of tephra in Quito. This volcano started to be active in 1981 with some phreatic explosions. At that time, when the volcano was erupting, we had a much smaller network, mainly formed by seismic stations. And you can see here this nice evolution of the activity with background activity in number of events per month below 100 when it was the background. Then we see the start of phreatic activity with the number of events per month being more than 300. And then we have the actual magmatic activity with events being even higher than 10,000 per month. The activity of this volcano produced important ash fallout in Quito several times in the last part of 1999. And we had, for example, the airport completely covered by ash, and of course, all the operation closed for several days. You also can see here people cleaning the airport using brooms. This activity, as I said before, lasted until 2001. And what was happening is that domes have been extruded in the crystal structure, and they were just collapsing to the west of the volcano without affecting the city by PDCs, but as you see, mainly by ash. This is the iconic photo of this eruption on October the 7th, when all the people from Quito could see this nice ash column of 13 kilometers height from the volcano. Almost at the same time, we had Tungurahua volcano erupting. It started in 1999. The activity lasted until 2016. And typically we had this kind of eruptive activity, ash and gases coming out of the volcano. This is how the monitoring network is working now. But of course, at the beginning of activity, we didn't have the same amount of instruments. Now the volcano is quite well monitored. And despite the fact that we don't have an observatory anymore, our observatory was some 15 kilometers from the crater, we have still all this data coming to Quito, so we can still monitor this volcano from the Institute. During these 17 years of activity, we could see some changes in the way the volcano was behaving. And for the first part of the eruption, we could see that activity was kind of more long-lasting, with eruptive phases that were lasting from weeks to months, and mainly characterized by this kind of activity of ash emissions. But since 2008, 2009, we see kind of a shift in this activity to more episodic eruptive phases. And the challenge with these episodic phases was that they typically started with this kind of big volcanic explosions forming PDCs. So from the monitoring point of view, it was quite more challenging to try to get a warning for this kind of events. During these 17 years, we had 9 PDC forming eruptions, so threatening people living very close to the volcano, or actually in the volcanic, on the volcanic edifice. But only one of these eruptions was, let's say, the paroxysmal one, and it was on August 2006. It was a BA3 eruption. The other ones were BA2 or less. And this eruption actually led 6 victims that got caught by pyroclastic flows. This eruption has been studied by several authors, and I just show here 2 nice sketches from Samaniego et al. 2011 and Myers et al. 2014. They analyze the samples of the rocks and minerals. So Pablo made a very nice petrological study of this eruption, and he concluded that this paroxysmic event was triggered by a recharge of mafic magma from a deeper reservoir. The same, or fairly the same, conclusions were obtained by Myers et al. In 2014. They also require mafic magma recharge to produce this eruption, and actually they also analyzed the eruption, or the samples of the eruption, in May 2010, and the mechanism, the triggering mechanism, was fairly the same. What was really nice in Tungurahua is that despite the big size of the volcano, people living around it just get very close together. They gathered actually to the volcanic activity, and they made this, they were able to make of this activity a quite important bond among people. So the Instituto actually was able to create, or to make born, this nice network of vigias, who is people that is living really close to the volcano, or as I said before, just on the volcano, because they have their outcrops there, their crops there. And they were also linked to the Institute by radios, and they were just reporting everything that they see in the volcano. Weather conditions, explosions, lahars, everything that was related to the volcanic activity. This communication proved to be extremely useful, especially when we had this sudden volcanic activity that could be, that was really threatening for the population. So this network is really useful. It's still working now. So we have contact with them from the Instituto through cell phone now, not through radio because we don't have a repeater, but we're still, they are still active, and they are still kind of working together. This kind of experience has also been transmitted to Colombia, to Galeras volcano, and to Chile's Cerro Negro in the boundary with Colombia, and also to Fuego in Guatemala. So we hope this kind of experience would be working as good as it were for Tungurahua during the activity. Then we had, almost the same year, 3 years later, the Reventador volcano made a huge eruption, the biggest eruption in the last century. It started on November 3rd, 2002. It was a subplinian eruption, BI4, with very few precursory activity. Nevertheless, I need to point out that at that time, we didn't have this monitoring network, and the activity was actually recorded in a seismic station installed for Cayambe volcano, some 40 kilometers to the west of Reventador. This activity produced an ash layer in Quito. Again, the airport completely affected. 1 to 2 millimeters of ash fall in Quito at that time. Of course, several days of the activities completely interrupted. This volcano is still erupting. Mainly the activity now is characterized by small lava flows, PDCs, lahars, and ash emissions, typically confined to this amphitheater. No activities coming out of this since the activity in 2002. We also had activity in Cotopaxi, 2015. This volcano is quite active, as you can see, this historic activity, at least 1 eruption per century, typically important eruptions. And taking into account that in 1877, at least 5,000 people died because of lahars being produced by the partial melting of the ice cap due to pyroclastic flows. This volcano has been monitored since the beginning of the Instituto Geofísico and even before. Actually, the first seismic station was installed in 1976, and it's the NASA station. And at that time, people was going to get the paper to get the records of the activity. So quite a nice story. But as this volcano is quite active, quite dangerous, the network was quite complete before the eruption in 2015, and it got improved even more with the collaboration of BDAP that gave us broadband stations, and Chalmers University that gave us 2 DOAS stations too. 2 more DOAS stations too. But as I told you before, we already have a nice network. So it was really important to count on this data to follow the evolution of this eruptive crisis. So I guess it's maybe the learning that we had in Tungurahua that led us build a nice evolution of the parameters for Cotopaxi. And actually the volcano was quite cooperative because the eruption was quite small and between BI1 and 2. And what we could see from the different parameters that we were monitoring is that the activity started, the precursory activity started with an increase in the number of seismic events. Then the seismicity changed to a tremor-like activity with variable amplitude. When this tremor appeared, we can also see here that the sulfur dioxide started to come out more easily. And in August 14, we had 4 hydromagmatic explosions that produce quite high ash and tephra columns. Ash was distributed mainly to the west of the volcano. After these explosions, we had the appearance also of BRO in the plume, indicating that magma was probably higher in the conduit. And then we had 3 phases of emission of ash. Here is shown the mass of ash that was collected thanks to the ash meters that we installed in the field. And it's nice to see how this amount of ash is quite nicely correlated with these 3 phases of tremor, with the amplitude of tremor. And we also have data about the height of the columns that were produced during this eruption, given that we had cameras, but also due to satellite information. So this eruption was quite well followed from the monitoring point of view. And actually it was the first reports of activity were sent to the authorities and population in April. So people at least know that the volcano was getting active. By the end of November, all the parameters were down, and nowadays we are back in the background levels. Sorry, but still we have the same monitoring network, so around 57 instruments monitoring Cotopaxi volcano. And at last, I will talk about Sangay volcano. Sangay is the southernmost volcano in Ecuador. It's a very remote volcano. Almost no people lives near this volcano. So the risk is not very high. It seems, and from the historical records that we have, that the volcano has been almost constantly active. And this seems to be the case at least from 2000 to 2015, where you can see here from the radiant flux obtained by instruments and satellites, but the thermal energy is kind of constant and quite low all the time. But then the activity actually shifted to a more episodic activity. We have 1 eruptive phase per year since 2015 until 2018. And now, since 2019, we expected to have one of these kind of small eruptive phases, but the volcano just decided to change again. And now it's still active until today with the same amount, with a big energy activity. So we have mainly the lava flows that are being produced in the volcano, but these were quite small in 2003, 2017, And after the eruptive phases ended, the activity was quite mild, mainly small explosions or ash emissions. But the activity since 2019 is actually characterized by a permanent lava flow that is going into a southeastern ravine, and that is actually eroding this ravine to a very deep and very large quebrada. And the lava flow is flowing through there. And sometimes when it collapses, it can go to a river, and now we have really some impact on the population living even 40 kilometers from the volcano. So now this volcano is posing an important hazard for population, and we need to monitor it better. For this, we actually get some instruments from BDAP this year, and these are being installed in order to get better monitoring of this activity. Nevertheless, with the stations that we had at Shanghai before this activity get increased in 2019, we were able to track part of the evolution of different parameters like seismicity. So we have more than 100 explosions per day. We also have satellite information from Tropomi for SO2 burdens, and also from our DOAS station that is 5 kilometers from the volcano. We also use satellite information, which I guess will be really important for this kind of remote volcanoes, to check for the formation of the volcanic edifice. We had this year 2 big events that actually were able to put ash in Santa Elena, some 280 kilometers from the volcano, on June 8 of this year and September 20 of this year. These events had no evident precursors, as the system seems to be quite open, so we need to be really careful about what's happening with this volcano. And the eruption is, of course, still ongoing. So as a summary of these 25 years of volcanic activity, we had 5 volcanoes in eruption: Pichincha, Tungurahua, Cotopaxi, and Reventador and Shanghai currently erupting today. These volcanoes have updated hazard maps. Actually, the last week we just gave to the mayor of the city the map of Pichincha that Patty Motis produced the last year. We also have instrumental networks with data streaming in real time, which is of course a minimum requirement when you make volcanic monitoring. And all the outreach information is public through our social networks and webpage. Of course, more information about the volcanic activity is available in several scientific papers produced by different researchers, not only our group. So thanks for listening to me. And as Diana said at the beginning, the Instituto Geofísico is extremely glad for having this award for volcano surveillance and crisis management. So we're very happy for having this. So thank you.
Thank you, Silvana, and I see applause throughout the audience. That was an excellent overview of the work you and your colleagues have done, both to understand the long-term evolution of the Ecuadorian arc, but also to observe some really interesting and frankly long-term eruptions, which I know is quite challenging from a monitoring and forecasting perspective. So this is a great talk. And I see we have a lot of questions. So if you have a question, please put it in the chat box. And I'm going to go ahead, Silvana, and just read these to you sequentially. So the first question comes from Clinton Coach. I apologize if I'm messing up names. And he just wants to know, this is concerning crustal assimilation. When you say upper versus lower crust, roughly what depths do you mean in those categories?
Well, the crustal, sorry, let's move to that slide. Right, too much. What? So, yeah,
just generally, what is upper and lower crust in
yeah, well, the crust thickness is quite variable in Ecuador, actually. So we have a thicker crust below the Eastern Cordillera volcanoes, and it's smaller or less thick below the Western Cordillera volcanoes. So we're talking about a crust of above around 50 kilometers here and 30 to 40 kilometers to the west. So I guess the limit between the upper and lower crust might be maybe 20 kilometers from the top to the bottom.
Okay, thank you. The next question is from Rebecca Morris, who says, I missed the first few minutes, so apologize if she missed whether you said what the dominant basement lithologies are throughout the arc.
Yeah, so actually for the western part of the arc, so the Western Cordillera is mainly oceanic terrains that have been accreted in 2 different episodes to the previous boundary of the South American plate. So these are oceanic terrains, mainly basaltic in nature. And for the Eastern Cordillera, we have different lithologies, metamorphic rocks, and then we have the Guyanese Creton to the more oriental part of the arc. So we have different lithologies all around the arc, and this also explains why we have very different compositions in the magmas, especially isotopically.
Interesting. Yes, very complicated place. The next question is from Gorky Ruiz, who asks if there is any plan to map and date the Chalpatán caldera area of northern Ecuador to see the influence of the Carnegie Ridge as it arrived in the subduction zone.
Well, not yet, but of course it's an interesting part of the art that we need to go to. Hopefully in the next years we have the possibility to do that kind of study, but no, sadly we don't have yet that information.
Yes, so stay tuned, Gorky. Kellen Wang asks, why is the volcanic arc so young? How old is the oldest part?
So the oldest part is, well, Chacana, up to 2.7 million years. But as you could see, the biggest stratovolcanoes started to form 600 years ago. Why is that young? It's hard to say. Maybe it has something to do with this complex subduction system. Probably Carnegie Ridge has an impact also in the age of volcanoes and in the productivity of the arc. Probably this ridge is actually bringing more fluids, producing more partial melting of this oceanic crust, and then making maybe better conditions to produce magma, and then it's quite productive. That's one of the hypotheses that we can use to explain that.
Okay, I had wondered about that, whether that relationship to the Carnegie Ridge was more mechanical or more compositional. It sounds like compositional, maybe more likely, as in terms of the influence on the productivity of the arc in that section.
Mm-hmm.
Okay.
Yeah, I think it's actually in both. So we have, of course, the arc that is larger at just above the Carnegie Ridge trace, but also you see this change in the geochemical parameters, which are different just in these volcanoes that are built over the Carnegie Ridge. So I think it's a quite important influence actually for all the volcanic arc.
So really a good demonstration of why thinking about the tectonic context of volcanoes is important. So the next question is from Antonina Calahorano. She wants to know, again, noting she may have missed it, is there any relation between the age of the volcanic complexes and the nice map you showed of lead isotopes?
Well, I haven't checked into that in detail, but actually I don't think so. As here in this map that is on the screen, you could see that these volcanoes that are, some of them are pretty old, like Chacana, but also young as Chalupas, 200,000 years, Cayambe also less than 400 years, display fairly the same composition. So at a first sight, I would say not strictly, but we can check that in detail.
Okay. And then I see 2 questions from Taimi Mulder. The first of which is, how long has it been since the most recent eruption on the extinct volcanoes? And on the potentially active volcanoes, how long has it been since they have erupted?
Well, we consider potentially active volcanoes when we have an eruption in the Holocene times. And I guess for these volcanoes, we are talking around 3,000 years, like Huicocha, Atacazo, Pululawa, the last, 3,000 years, the last eruption of these kind of volcanoes. And then for the extinct, let's say, Chalupas would be a good approach. So 200,000 years.
Okay. And just, I think we'll take a couple more questions at this point. So Taimi has a second question. What is the boundary or definition between potentially active or active? You've sort of addressed that. Some of the reading I've been doing indicates that there may not be as many extinct volcanoes as we previously thought. And to my mind, this comes to like Chomadul in Romania and evidence that some extinct volcanoes might actually still have active magma.
Actually, that's interesting, because the more we study the arc and the more we have more dating of the arc, we realize that most of the, let's say, the blue volcanoes which we consider extinct changing to yellow volcanoes, so potentially active volcanoes. So it's actually depending on, it's not a fixed characteristic. The more we study the volcanoes, the more we know about it, about them, and sometimes they change their label. So they move from non-active or extinct to potentially active, depending on the studies that we have. So it's
highlighting. I'm sorry to cut you off. Just highlighting that actually extinct volcanoes deserve additional study, not just the potentially active. It's a very good point. John Lyons asks, is it correct that the local observatory at Tungurahua has been closed? And if so, why? And if I'll leave it to you whether you want to answer that question or just maybe follow up with John if you'd prefer.
No, sure, I can answer that question.
Okay.
It was a really nice place. I guess all the people that had the possibility to be at the Tungurahua Volcano Observatory enjoy a lot that infrastructure that we had there. It was really nice, great view of the volcano and nice communication with all the community. So really a perfect place to be. But the volcano stopped its activity in 2016. We keep the observatory running until 2019, so 3 more years after the volcano stopped its activity. And then actually, it's really expensive to keep that kind of infrastructure working all year long, and it was not possible anymore to justify all these expenses for a volcano that was not active anymore. So of course, all the monitoring network is still in place. So all the data is arriving to Quito. We are just not us as researchers or technical staff at the observatory. But if something happens, we hope we can quickly move there and install a new infrastructure to watch Tungurahua from closer.
Okay, and then this is the last question, which is from Ana Martinez, asks, what is triggering the episodic events? Do the evidence suggest it is driven by crustal or mantle process?
Well, the episodic events in Tungurahua, we actually made an interesting research about that. And it seems that it might be actually more like upper level conduit conditions and how the magma becomes more and more viscous and actually stiffens and make a kind of plug. And then as gases are still there and the magma can be actually crystallizing, getting more warm as crystallization is being produced, then we have a kind of a renewal of activity by blowing up this plug. So this is kind of a sequential process that can take due to the crystallization of magma in the conduit, a stiffening of the magma, and then blow up of the plug that is being produced. That's kind of one of scenarios that we can consider for this kind of episodic activity.
Yes, okay. Okay, and I see many people thanking you for your great answers to their questions in the chat and for this excellent talk. A round of applause, everybody. Thank you again, Silvana, and to your colleagues. This has been really fantastic, and we're very grateful for you to spend the time and talk with us today. So round of applause. Thank you from all of us.